time in our future, or it's on another side, and so on. There are bangs and bangs and bangs forever. The theory was now complete. Two brains come together, inject one another with energy. Then dark energy takes 1 trillion years or so to spread that energy out. The brains crash and then come together again. This cycle happens endlessly. Idea.
It's certainly the case that when W. Matt made this announcement, the way most people interpreted that announcement was it's beautifully consistent with the Big Bang inflationary picture. To us, it meant that the cyclic moment in the game is as much as inflation was.
WMAP scientist David Spergel is certain of one thing. The answer will be found in the data collected from our own cosmic history.
By looking at these details, we should learn about physical processes that generated those fluctuations. Were they generated during a period of rapid expansion like inflation? That's true. What we expect to see in the simplest form is a pattern that follows a nice bell curve. However, if something more like cyclic lines happens, we'd expect to see additional patterns and correlations.
But what happens over time is one theory becomes more and more complicated, and the other theory remains simple. And usually the simple one that's able to explain things simply, wins in the end.
But which theory is right? The answer to one of the biggest cosmic mysteries of all, was there a time before our time? We are circling the Earth many miles over our heads. Did a big bang suddenly and inexplicably burst into life from a time of no when and a place of nowhere? Or could we bounce from the contraction of another universe that existed before ours? Or are we living 1 trillionth of a trillionth of the width of an atom away from a parallel universe? And every trillion years, these parallel worlds bump into one another and fill each other up with huge amounts of energy and matter. Professor Martin Boyerwald's mountain universe is still a work in progress. But for proponents of the cyclic and the Big Bang inflation model, the answer to how and when the universe started may be moving toward us across time and space like tiny ripples in the cosmic ocean. Gravitational waves.
Gravitational wave is pretty much like a sound wave. We're used to a sound wave traveling from ECUs at speed. As a compression and expansion of the air between us, so the molecules get more densely packed and further apart as the wave moves from ECU.
But gravitational waves ripple not air molecules, but space itself, which means that they can stretch out or compress a beam of light and cause a shift in its color.
So if space expands, we'll see the radiation shifted to red frequencies, longer wavelengths, but if it's coming towards us, we'll see it slightly bluer than it would otherwise have been. And so by carefully analyzing the pattern of radiation on the sky, we can in fact infer if there are gravitational waves traveling through our part of the universe.
Temperature measurement of the radiation pattern will tell us if there are gravitational waves. But it is the polarization of these waves that will tell us their size.
Gravitational waves imprint a distinctive pattern of polarization across the spectrum. Unpolarized light is equal number of photons lined up this way, or this way. But light can be, and actually often is when it scatters off on the surface, polarized.
For cosmologists, the trick is figuring out how to measure this polarization. As rocket technology will get the scientists far enough up into space to spy these gravitational waves.
The Planck satellite is expected to WMAP. It will be measuring the stars about twice the resolution, about 10 times the sensitivity. And if we're lucky, that'll tell us what happened during the first moments of the Big Bang.
For proponents of the Big Bang inflation model. Finding significant gravitational waves would be the final step in proving that there was a giant expansion of whooshing energy from a place of nowhere and no when. But Paul Steinhardt and Neil Turok are also looking forward to the Planck satellite results. In their cyclic model of the beginning of the universe, two brains coming together would be a much less intense collision, and the chances are that gravitational waves would be almost non-existent.
If we observe these gravitational waves in the Planck spike, that will support the inflationary theory and rule out the cyclic picture, and converse, if we don't see them, that would strongly support the cyclic picture.
Already, the battle lines are being drawn. At a 2001 conference on M-theory in Cambridge, Neil Turok was asked to give a talk on their new cyclic model. Once again, the controversial subject of gravitational waves was raised. World-famous physicist Stephen Hawking was in the audience that day.
I'm explaining our calculations, and in particular, the conclusion that we did not expect to find gravitational waves. And so Stephen piped up in the middle of my talk, and he said, I'll bet you're wrong. And so I was taken aback, but it's not unusual for Stephen. He's a very forceful person. He has strong opinions, and he's not afraid to stick up for them. But on the other hand, I have thought long and hard about this problem, and I wasn't ready to concede. So I said, okay, I'll accept your bet for any amount you care to wager at 50-50 odds, and we'll see what happens.
But no matter which description of the beginning of the universe appears to be more accurate, the true winner will be our own scientific understanding.
Yeah, to me, it's man against nature. We're trying to figure out nature's secret. If we're lucky, we'll be surprised.
These tiny, almost undetectable waves will have a tsunami-like effect on the future direction of cosmology. Instead of appearing from nowhere and no when, and rising from stardust to humankind, we may have to consider the mind-boggling premise that we are just the latest version of an endless series of universes. We still might not know what happened before the beginning, but we would know that something did. The final answer may be close at hand.